So you decide to play a slot machine. As usually expected, you spin it and find out that you have won nothing. Turns out the odds of winning this particular jackpot are 1 in a million. Hardly likely. But then you get the genius idea to play it 1,000,000 times. Statistically speaking, this would pretty much guarantee a win. Or would it? In a basic coin flip, there is a 1 in 2 chance for the coin to come up heads. If you flip a coin twice, you can get a head, then another head, a head then a tail then a head, or 2 tails. Now we notice that there was a probability to flip a coin twice and get no heads, even though we just said the heads are 1 in 2 chance. In fact, the odds of getting any at all seems to only be 75%. Well, that's because the 1 in 2 is describing a long-term average, not what we expect to happen every single time. But this is a boring example. So now say that every day there was a 1 in 3 chance that a cat shows up to your front door. I couldn't think of a better example, okay, so just stick with me. Also, every day is independent of the last. That is, if the cat shows up one day, that doesn't make it more or less likely to show up the next day. This cat operates on an unpredictable schedule. All we know is that this cat is expected to show up once every 3 days on average. But what is the probability that this cat actually shows up at all in those 3 days? We can figure this out by finding the probability of the cat never showing up. On each of the 3 days, the odds we see no cat is 2 and 3. Since these are independent events, to get the total probability, we can just multiply 2/3 times itself 3 times, 1 for each day, which is about 29.63%. If we subtract that from 100, we get the probability of the cat showing up at least once within 3 days to be about 70.37%. Interesting. It appears that the probability went down, and the probability the event fails went up. So the obvious follow-up would ask what the probability is of a 1 in 4 probability occurring within 4 trials. We can figure this out the same way. The odds of it not occurring is 3 and 4, then we raise that to the 4th power and subtract that from 1. This time we get 68.36%, another decrease. So the odds of failing are now up to 31.64%. So does this mean the probability of failing will keep going up? Maybe to 1/3, maybe to 100%, beyond 100%. Well, of course not. That doesn't even make sense. If you read the title of this video, you might know the answer. I mean, we have this formula where n is the number of trials, and 1 minus n over n is the probability of failing. So we want the limit as n goes to infinity. And it turns out to be about 0.36788, or say 47%. This is an important value in probability theory. So within playing that slot machine 1,000,000 times, you only have about a 63% chance of winning back the $1,000,000 you just spent, and a 37% chance of not winning at all. So here is the claim we have. A random event happens once every n number of trials, on average, and we attempt n number of trials. Then as n approaches infinity, the probability that we still see 0 successes is about 47%. Mathematically, the number we calculated is like this. The probability that an event doesn't occur multiplied by itself n times. This LIM thing just represents that we want n to be infinitely large. We can also rearrange this equation to use the probability as an input and the number of trials as an output. This exponent represents the number of trials, so we can make that a new variable, say t for trials. Then we can use logarithms to get the t by itself, and this looks cleaner using the change of base formula. So now we want to know how many slot machines, each with a 1 in a million probability, we need to play to have a 99% chance of success, or a 1% chance of failure. Have the log of the chance of failure divided by the log of the chance of failing a given trial, giving us about 4.5 million trials necessary to have a 99% chance of winning. So now you might be thinking, 47%? Seems a bit strange. Like it doesn't represent a nice fraction. It's close to 1/3, but isn't. So where was this number coming from? Well, let's take the reciprocal of that exact value. And when we do that, we get 2.71828. Oh wait, that's E. Euler's number has been hiding within, and 1 over E is about 47%. E represents the maximum 100% growth that can occur exponentially. Say you have 1, then multiply it by itself plus some increase, say 1/n of it, and you do this n times. As we increase 1 by a smaller and smaller amount, more and more times, this growth factor approaches E. This is what E looks like mathematically. If we invert this, aka take the reciprocal, this n exponent becomes negative, then we can combine 1 plus 1 over m with a common denominator to be written as m plus 1 over m. Then we can factor that negative m exponent to get this, then we can do this, and we end up with this. But this is a bit strange, so we can let m equal m plus 1, which means m equals n minus 1. So by substituting m's in, we get this. Now this plus 1 in the exponent actually doesn't change the limit, because n is going to infinity anyways, and adding 1 doesn't change that. So this is the same thing as this. And would you look at this? Using algebra, we have ended up with the theorem we had before. Unfortunately, beyond the mathematics, there really is no simple intuition to how E relates to this probability that I know of. Maybe there is, and I'm just an idiot, so if you have any ideas, leave them in the comments. But the important thing to note is the importance of 47% in probability. In fact, it's so important that there was a mathematically proven rule of thumb called the 47% rule. This rule states that when choosing from a set of things one at a time, it is optimal to reject the first 37% of them automatically, and then start comparing the rest to those 47%. For example, say a pet shop has 100 cats. I'm going back to cats. And you want to choose the best behaved cat. So you interview them, one at a time. And after each interview, you decide if that's the one to accept or to reject. The 37% rule states that you should interview, but reject the first 37 cats out of these 100. Then you choose the first cat that is better than all of those 37. I won't go into the exact mathematics behind this because it's a bit insane, but it all ties back into probability theory. And if you're interested, Number File has an excellent video giving a more in-depth explanation of this through an example of choosing toilets, of all things. But anyways, this video is getting long, so I will see you in the next one. Thanks for watching.